second example for the context that might be a useful pattern and you could actually use if you're implementing your own multidimensional array. So the goal is to implement the indexing of a multidimensional array in a generic way. So with arbitrary dimensionalities, with stride computation happening at compile time, and when all the dimensions are compile time constant, and with the same code, compute the indexing at runtime when the dimensions are runtimes. So we have to implement this index function returning the index of the storage given the dimensions, the I, j, k, and so on. So this is the main would look like this. The class which we will implement is storage info. We pass the dimensionality and the 3 dimensions. And then we access the indices, specify 3 coordinates. And these coordinates will return the offset at which we access the storage. So this is something, this is a simplified example of what we implemented in our own library for domains in our own specific language here. And after the exercise that will be at the end, it will be basically a clean of what is the real thing which is in the library. So this thing can be instantiated. This instantiator is not a constant expression. This one is a constant expression. So with the same API, you should be able to do both. So don't get scared. So the only thing which we will use is this last thing. So this is the formula to compute the indices. So we have the coordinates as a pack of integers, and then we will return the coordinates n, which has stride 1, plus this is the stride for the first coordinate, this is stride for the second coordinate, and so on. So everyone should be familiar with that. We can rewrite this in a generic way with this sum and then we can factor in this sum the dimension n, and we can write it exposing n minus 1 so that we have a recurrence relation. And we can write this recurrence relation in a recursive way. So this is what we will implement. This recursion formula is what we will implement. This gk will be coordinate 0 in case k is 0, or it will be expressed in terms of gk minus 1 if k is bigger than 0. So this is a reminder of the GT integer sequence. I hope it was clear for the previous in the previous slides. So we have the variadic templates, and we know how to put that, how to pass that to the index. So the variadic template is just to pass arbitrary number of variables in your API, and the integer sequence is to do such things like zipping. So we want to assign an index to each element of our pack. So in this example, we have 2 packs. So one will be the integers, the dimension, the coordinates which I'm passing to the index function, and the other one will be indices from 0 to the dimension of the second pack. And we want to zip this too. So we want to write pair of the first dimension 0, then a pair with the second dimension 1, pair with the third dimension 2. To do this thing, we pass a std integer sequence as an argument. So this is the same example as we saw before. So we will use this now. So first thing, we implement the class without the index method. So this is you can open in the storage folder. There's a main.cpp. So we can open that. So let me just, this is the final interface. I just comment out this part. So what we have here is a storage with a const-text preconstructor, which accepts a variadic number of parameters, arbitrary number of parameters, and initializes this array of dimensions with the pack. So I will have this size is the template argument, and this will be initialized with this variadic pack. Does not check here that the length of this pack is the same as the size template argument. I didn't add protection for the simple example, not to pollute the code, but there should be. So this thing should work as it is. Try to compile it. Shell. Storage main. So it works. It doesn't print anything. So now, next step is to build the get method, the index method, to compute to get the index. So first, we want to give the index method this interface. It has to take the coordinates. So we don't want to put a std integer sequence here inside, because this is the thing that the user will call. The user wants to call this, passing only the coordinates. So we get an helper function which we call edximpo, where we pass as an argument the std integer sequence with the size of the parameter pack. So all the complexity is in this idximpo. So now, what we have to do is that we have to implement this thing, this recursive thing. So we have to pass all packs. One pack is the pack of the coordinates, and the second pack is the pack of the indices. So the indices are k, and the coordinates are chord, and they have this meaning in the formula in the formula here below. So first we will see how the implementation of the first one is. So we have here, we pass one pack, and we identify the first element of the pack and the rest. So we split the two, because we will assume the first element of the pack. And we do the same thing with the coordinate. So this is the k, and this is the coordinate here. So we work on the current k and the current coordinate. Then we have the signature of the eximpo accepting an integer sequence and the coordinate. So first coordinate will be the coordinate we will iterate on in this case. And here we implement these operations. So first chord is chord k, then emdings of the current on the current k is this one, and then we have the recursive call. So here we call recursively this method by passing only rest k. We don't pass the first one. We only pass the rest of the parameter pack. And the same thing for the coordinates. We don't pass this first chord. We only pass the rest. So this is the basis of the recursion. So here was. So we can add these two to our example. So index. This is the one which was in the previous slide. And strides. So let me put it here. So now we implemented the recursive part, this formula. Then in a second, then to stop the recursion, we have to implement the stopping condition. So this is the two parameter packs. Now there are two elements, and we have IDX info, which takes two arguments. One is an integer sequence with only one number, which is the 0, and the coordinate is coord 0, and we just return coord 0. So we add also this. Version. Okay. Now we can try to uncomment this. Compile. So these are all static asserts. So the fact that it compiles, it means that these are the results are correct. So I can I can also put other numbers here which are not 1. Which like the only important thing is that it stays in the region defined by this. And this is completely arbitrary in the dimension, and is the same regardless if this storage info is a runtime or a const or a constant expression. And where's the mouse? No. Okay, so this is very useful to have a compile time indexing. It's very good for efficiency. You want to access in constant time, specifying the dimension and having the offset at which you access the storage being computed at compile time. It's very good. And so this is the main. Now, the exercise would be to abstract the memory layout. So often in high-performance computing, we need to adapt our memory layout to the architecture. So we cannot fix that because maybe if we run in one architecture, we need one memory layout where the stride 1 is the first component and the last one has the biggest stride. But maybe in another architecture, like for GPUs or accelerators, you might have the other way around, or you cannot fix. So what we really have in our library is a generic way to specify the memory layout. So the user specifies layout map, which is a type, and it says I give 0, 1, 2, 1, 3, 2, for instance, if I want the smallest stride to be I don't remember which is the smallest stride. Yeah, in this case, the smallest stride is where there's a 0. So the last dimension has the smallest stride. So if I put a 1 here, my index function returns 1. The 1 is the second biggest, is the second smallest stride, and so on. So this is the exact reversed order with respect to the example we had before. So before we only had to specify the dimension of the storage, and the layout was automatically assigned as 0, 1, 2, 3, 4. Now we want this to be specified by the user. So to implement this, you don't do because there's already this. You can follow the instructions in the storage info.hpp file in the examples code, and there's already where there's already the layout map.hpp file, so you don't have to implement that, and there's already some instruction on the parts which you will have to change. So does anyone have any question?